All right, so today I'll present some work I've done with collaborators on trying to constrain the properties of the quark-gluon plasma. All of this using measurements from Hebbian collisions. I forgot to ask how it usually works. You're welcome to ask questions during the talk if you feel like it. It's no problem at all, but of course I'll be happy to answer any questions you have at the end. So let me jump right in. So we know that in normal, let's say terrestrial conditions, quarks and gluons are confined into hadrons, like protons and neutrons. We also know from experiment that quarks and gluons, if the stronger the interaction energy between quarks and gluons, the weaker they interact, which is something that is called asymptotic freedom. So I'm sure you're all very familiar with this figure here from the review of particle physics, where you have different measurements of the strong coupling constant of quantum hydrodynamics. And it shows how the interaction strength decreases as you increase the interaction energy. Now, the scale that determines what is a large energy here is this lambda q here, lambda about 200 MeV. And here it roughly looks like there's an inverse dependence of the interaction strength with the interaction energy, but that's because the scale here is on a log plot. So what you effectively have is a inverse logarithmic dependence on your interaction energy. That means that, at least in theory, there's a way to arbitrarily weaken the interaction strength of quarks and gluons. And the way that you can do this is to make sure that they constantly interact with a very high energy. And by very high, I mean extremely high energy, if you want to talk about a relatively free gas of quarks and gluons. Now, we can use the following thought experiment. Imagine that you have a gas of hadrons, a box of hadrons in equilibrium. And they're in equilibrium at a given temperature. The temperature roughly sets the scale for the energy of your interaction between your hadrons. Not at higher energy, the energy of interaction between your quarks and your gluon. Now, we know that at some temperature, you expect that you'll have a transition from your normal hydrodynamic matter to your quarks and gluons. There's a couple of different ways of estimating this temperature. First, we know that lambda QCD is about 200 MeV. That translates into a temperature of about 10 to 12 Kelvin. That's, of course, an enormous temperature. And that's what we should expect from just observation. We know that, of course, nothing on Earth, that quarks and gluons are confined on Earth. So any temperature that is, it's a terrestrial scale, is way too low. And we also know that pretty much everywhere we look in the universe, even if we look at stars or extreme astrophysical events like supernova, we're always talking about hydrodynamic matter. Except for very, very special cases, we're always talking about normal hydrodynamic matter, which means that the temperature at which this transition happens from hadrons to a plasma of quarks and gluon is much higher than pretty much anything that we have naturally in the universe. Now, if we want to go to an extreme and find a temperature where we have a quark-gluon plasma, or at least we had a quark-gluon plasma, we can always go to the early universe, where we know that for an instant after the Big Bang, we understand that the universe was filled with the plasma of quarks and gluons, and the temperature were high enough that you could think of the plasma as a weakly coupled quark-gluon plasma. Now, the plasma that I'll be discussing today is not this weakly coupled plasma, but it's this strongly coupled quark-gluon plasma. So because you have such a slow running of the coupling, this is a region where you have this transition from normal hydrogen matter to a quark-gluon plasma. But the interaction within the plasma are still very strong. So you're very far from describing, from looking at a gas of weakly coupled particle. You really have a strongly coupled medium. And this is not necessarily a distinction that is made. I think it's made more often nowadays. But there's a very large distinction between having this a weakly coupled quark-gluon plasma and a strongly coupled quark-gluon plasma. In the weakly coupled case, because the coupling is small, you actually can compute from first principle many of the properties of a plasma. You can determine the thermodynamic properties of a plasma by protective calculation. It's not trivial. There are significant a number of complications, but it's well understood nowadays. And you can even compute properties like the transport coefficient, the rate of emission of electrons or photons from a plasma like this. So for a weakly coupled quark-gluon plasma, we actually know quite a bit from pure theory, just from knowing how to do high temperature quantum field theory. But a strongly coupled quark-gluon plasma, it's very different. Now, if we rephrase in a sense, the thought experiment I had here in terms of a phase diagram, here I'm showing a very simplified phase diagram of nuclear matter. We have here, the axis here is the temperature, and the other axis is the baryon chemical potential. So what I've been discussing up to now is mainly this high temperature, low baryon chemical potential region here. And that's really what I'll focus on today. It's not that the other regions are not interesting. I'll come back to this in a slide. Now, in this region, we actually know quite a bit about the phase diagram about the thermodynamic properties of the plasma, even the strongly coupled plasma. And we know this thanks to calculations that have been done in fine temperature lattice QCD. So I think many people here, most people here are familiar with this kind of calculation. And over the past 20 years, there's really been a huge increase in the accuracy of these calculations. And now this blue line I'm showing here for the pressure over the temperature to afford as a function of temperature, you can see that we have a very good calculation of this pressure and these temperature here, just for reference. Below about 160 MeV is where you should start thinking about normal hydrodynamic matter, so a gas of hadrons. And above about 160 MeV, you have a strongly coupled plasma of quarks and gluons. And you can see that calculation that uses hadron here. So there's a way to calculate using the hadron resonance gas and similar models. There's a way to calculate the properties, thermodynamic properties of the plasma. And you see that they match very well lattice calculations. And the lattice calculation show here that there is this crossover from, so there's no sharp transition from hydrodynamic matter to this plasma, this strongly coupled plasma of quarks and gluons. There's a slow crossover. And eventually these calculations, these lattice calculations match per-derivative calculations that are done using quarks and gluons as degrees of freedom. Now, of course, there's still a lot to learn about other regions of this phase diagram. I concentrate on this region today, in part because it's the region that we probe in very high energy collisions of nucleus, which is where the measurement I'll be discussing today are from. There are ways to look at different regions of this phase diagram with collisions of nucleus. If you look at lower energy collisions, or you look at different regions of space, so high rapidity regions of your nuclei, you can actually probe higher baryon chemical potential and somewhat lower temperature. So you can probe this region better. And if you go to even lower collision energy, the type of experiment that will be done at FAIR, for example, in Germany, you can probe even lower temperature and even higher regions of baryon chemical potential. Now, eventually, of course, you start making connection with astrophysics, so nuclear astrophysics. So you have the neutron star that has a large baryon chemical potential, but a low temperature. And if you start looking at neutron star merger, for example, then you're looking at a region that has a somewhat higher temperature and still very large baryon chemical potential. Now, the exact degree of overlap of these regions, I think it's fair to say, still unclear. But there's more and more work being done in the field to try to apply techniques that are being used in let's say, to study the equation of state in one region and apply them in other regions. So there's more communication, I think, between the field of invariant physics and nuclear astrophysics. Now, as I said, in this region, we actually know in these regions, we actually don't know very well what the equation of state is. But I'll focus today on this region, where we know what the equation of state is. And what I'll be focusing on is not the equilibrium properties, it's the near equilibrium properties of a plasma. So equilibrium properties is the thermodynamic relations that I've been the thermodynamic result I've been showing. Now imagine that instead of having your equilibrated plasma of quarks and gluons, you look at sound wave propagating into this plasma. Now these sound wave will propagate at a certain speed that's given by a speed of sound. That's known from thermodynamic calculation, from the same lattice QCD calculation that I've been referring to earlier. But there's more. Depending on how your medium responds to deviation from equilibrium, these perturbations will dampen either faster or slower. And this decay of the perturbation here is related to the transport coefficient of the medium. They're related to, they characterize how the medium responds to deviation from equilibrium. And those are additional information, additional degrees of freedom for your, not additional degrees of freedom, they are additional characteristic of your plasma. So they're not given by your equilibrium properties, they're complementary, and they're what we call real-time properties. And importantly, we cannot compute them accurately yet, or they cannot be computed accurately on lattice. So the aim, so what I'll be doing today is describe how we can constrain those from measurements. Now, there's a very strong connection between the value of those transport coefficients and the strength of the interaction of the plasma. Now, this mapping between the coupling and the viscosity is always somewhat confusing. So strong coupling is small viscosities, weak coupling is large viscosity. Think of it as, if you think of it as the sound wave, think of it as the ability of the medium to sustain collective behavior. So if you have a perturbation, a sound wave, and you want it to propagate over a large distance, this wave is a collective property of your medium. So it's not that one particle is propagating over a large distance. It's that the wave is propagating over a large distance thanks to the strong interaction between the different parts of your medium. So that's why you should think of as strong coupling as the ability of propagating information over a large distance, which means you have low dissipation, you have small viscosities. Now, one of the, I think, better known result about the viscosity, the relation between the viscosity and the strength of the interaction is from calculations that have been done, not in QCD, but in a different theory, in a different field theory that has been done in unequal force per symmetric Yang mass. Now, that's a theory that has a higher degree of symmetry than QCD, has different degrees of freedom. But it has the benefit of having we can use holography to study the strongly coupled regime of this field theory of unequal force super Yang mass. And it's possible to compute the shear viscosity in this limit. Now, again, in the weakly coupled limit, we can always use weakly coupled technique, perturbative technique, to evaluate the shear viscosity. You can do this in QCD, or you can do this in unequal force per symmetric Yang mass. And as we've just discussed, in this weak coupling regime, the viscosity is actually quite large. Now, for QCD, we don't know what the viscosity is at large coupling. But in this case, they computed that you can see the result here, the red line. And this 1/4 pi that's very famous is the asymptotic result when you take the coupling, the tough coupling to infinity. So it's not the viscosity of, it's not actually a viscosity of the plasma, it's the limit, the minimum possible viscosity of the plasma. Now, as I said many times already, I'll be discussing how to extract the viscosity from data. I just wanted to say a few words. So we can compute the viscosity in theories like ADS-CFT here. There's a number. So in the weakly coupled regime, the viscosity has been calculated for QCD. And there's a number of different approaches that have been used to calculate the viscosity of QCD in the strongly coupled regime. But those are, in a way, model dependent. You need different approximations. And it's still very much a work in progress, especially if you talk about this region here, where you have the confinement, the transition from 100 degrees of freedom to a plasma of quarks and gluons. Now, again, the idea is not that we should replace, that we should not compute it and we should simply extract it, but we should certainly try to do both to see if we can get an agreement. So perhaps you've heard in the past of different people trying to compute the viscosities from first principle. People are attempting to do it even with holography, with modified version of field theories that are not QCD, but that can have a dual just like this. If you have questions at the end, you're welcome to ask, but I won't be discussing this in any detail. The only thing I want you to remember is that we want to compute it. People are trying to compute it in QCD. We're just not there yet. So what I'll be discussing is how can we measure it from data taken in heavy ion collisions. Now the data is coming from two facilities. We have the relativistic heavy ion collider on Long Island, and we have the Large Hadron Collider in CERN. They all have an array of sophisticated detectors. And effectively, the experimental setup is that you send two nuclei that are ultra-relativistic. They have kinetic energy that is hundreds to thousands of times larger than their mass. And these nuclei collide, and they produce thousands of hadrons, photons, electrons. And that is what is picked up by detectors. And what you want to do is to understand the properties of a quark-gluon plasma by studying these shower of particles that are coming out of the collision. Now, these detectors actually, I mean, we say one detector, but of course they can measure multiple different particles. They're in a sense a composition of multiple detectors. They can measure charged hadrons, They can measure electromagnetic probes like photons and electrons. And they can measure, some of the detectors can measure muons and can also access indirectly electroweak bosons through muons. So in a sense, we're doing all our multi-messenger study with a single detector, unlike in astrophysics application, where often you will have, even for different electromagnetic spectrum, you'll have different detectors. And of course, you use gravity, which we don't use here. You can use gravitational wave nowadays for astrophysical application. So this is our version of multi-messenger physics and trying to learn about the properties of nuclear physics by combining the information carried by all these different particles, all these different messenger, and finding a consistent theoretical description, consistent viscosity, for example, that can describe all these particles. Now, how do we do this? As I said, the experimental setup is basically this one, but nowadays we have a very good understanding of what happens during a collision. And what happens is that because you have so much energy in those initial two nuclei, you can really concentrate a huge amount of energy in a small spatial area, which means that you can create regions of very high energy density, which is, as I've discussed before, which is this setup that you need to free the quarks and the gluons for an instant from the hadrons and create this plasma of very dense matter. Now let me walk you through these different stages. So the nuclei are highly Lorentz contracted, they collide. There's a large deposition of energy coming from this kinetic energy of the initial nuclei. This forms a plasma of quarks and gluons. The initial stage, the initial phase of the evolution of this plasma is actually quite complex. But eventually, this plasma undergoes a relativistic hydrodynamic expansion. It expands for a short amount of time, and then because it expands, it very quickly cools down, reconfines into hadrons. These hadrons keep interacting, and eventually these hadrons are what we pick up in the detectors, what is being measured. Now, as you can see, there are multiple phases of collision, and all these different stages, in a sense, are different many-body settings of nuclear physics, of QCD. The way you describe the collision of nuclei, the information you use to describe the collision of nuclei is very different from how you describe, for example, the evolution of the quark-gluon plasma, and how you describe the later interaction between hadrons in the later stage of collision. The challenge is that you have to describe most of these stages very well if you want to access the properties, the equilibrium and near equilibrium properties of a plasma, which you really have access through this hydrodynamic phase here. So that is the real challenge of constraining the properties, the viscosities of QCD from heavy-end physics, is that you control what you send into a detector, you measure something, and you need to describe essentially all the different stages of a collision to even access one part, the properties of one part of the collision. Now, there are sophisticated models that are being used to model this early stage of the collision. If you have questions later, I'll be happy to answer any questions you have about them. Let me skip to what the energy density looks like roughly at the moment where you can start describing the plasma as a fluid that is expanding. So this is an example of energy density profile that I took from this work I've done with colleagues in the US and in Canada. And you can see that the energy density that you have is, so just for reference, 0.121 is roughly where the transition happens from hydrogen matter to a quark-gluon plasma. And you really reach locally very high energy density of tens to hundreds of GeV per Fermi cubed. These correspond to temperature from about 200 MeV, 150 MeV to 300, 400, 500 MeV locally. The shape of a plasma, the fact that it has a certain shape is very simple. It's really simply from the fact that your nucleus don't necessarily overlap perfectly. So you have this football-shaped region that is produced. So the plasma is produced in this typical geometry. And the fact that you have a fluctuation comes from the fact that, of course, your nuclei are not just diffuse lumps of quarks and gluons. You have the nucleons inside, and every collision will effectively have fluctuation in how energy is deposited from the position of the nucleon, and even some nucleonic fluctuations. So you have all these fluctuations that you have. They determine your how you initialize your hydrodynamics. And then you follow the evolution of this plasma using relativistic hydrodynamics. Now let me walk you through briefly the equation or the basics of relativistic hydrodynamics. Now here, I've emphasized a couple of times already in this talk, the connection that the field has with nuclear astrophysics, for example. When we say relativistic hydrodynamics heavy ion collision, what we mean is that the fluid is moving at velocities that's non-negligible compared to the speed of light. So we're talking about special relativity. Of course, in nuclear astrophysics, they have to, in neutron star mergers, for example, they have to worry about actual general relativity. This is not something we have to do, but in both cases, we have to worry about special relativity. You can think of relativistic hydrodynamics as the evolution of your energy momentum tensor. Your energy momentum tensor is simply defined by your energy density, which is a local quantity. I was showing the field in the previous slide. You have the flow velocity, the velocity of all the different parts of your plasma. And if your medium is not in local thermal equilibrium, but there's some deviation from local thermal equilibrium, then you have additional components. You have your bulk pressure and your shear tensor, or a viscous part of your energy momentum tensor. And your relativistic hydrodynamics is a conservation of this energy and momentum, this conservation of energy and momentum. The pressure here that enters is given by your equation of state. And nowadays, we don't try to extract the equation of state from data. We simply use the excellent calculation that we have from lattice QCD for the thermodynamic properties of the plasma. So this is an input in our model. Recall that we're still only looking at a very narrow region of the phase diagram. And if you're looking at different regions of the phase diagram, you actually need you need additional, you need to describe additional quantities. You need to describe the conservation of your baryon density. So what I'm describing here is assuming that you have a zero net baryon density. Now, what we use in heavy ion physics is second order viscous hydrodynamics, which, if you're familiar with the field, we call them Euler-Israel-Stewart and relativistic hydrodynamics. So if you're familiar with non-relativistic hydrodynamics, the equivalent of, so you have ideal hydrodynamics, which is well defined in the relativistic and non-relativistic case. Then you have Navier-Stokes hydrodynamics, which is the non-relativistic viscous case. Now, in the relativistic case, the Navier-Stokes, the simple first-order hydrodynamics has issues, and typically we don't use this Navier-Stokes version, which would just be this expression here, but we use the second-order version, which have additional terms. So it's a relaxation type equation for your bulk pressure, your shear tensor. In practice, these equations are implemented in codes. If you're familiar with the field, it's codes like music and Vishnu that solves these equations in full 3+1D dimension using finite element methods. Now, we've been using hydrodynamics to describe the evolution of the energy momentum tensor of the quark-gluon plasma for years now. It's not that there hasn't been development. There's a better understanding now on how to derive these equations of motion in second-order hydrodynamics. You can see 2 papers here about 10 years ago that were published about 10 years ago. And much more importantly, there's still a lot. I don't want you to think that the application of relativistic hydrodynamics in heavy ion collision is just run of the mill. It's actually, there's a lot of development on the hydrodynamic side. People recently have been looking at the hydrodynamic equations that we've been using for some time, and they've identified issues with causality and stability for certain modes of the equation. And they've also been, there's been work in trying to put forward first order hydrodynamic equation that don't have those causality and stability issues, that have very similar, that have essentially the same behavior for long wavelength, so for long scale features of your plasma, but that have better behave evolution for the shorter wavelengths of your plasma. There's also a lot of work being done on trying to better understand the regime morphality of hydrodynamics. If you're in the field, I'm sure you've heard a lot about attractors and so on. So in a way, we're using, in the same way as we're using hydrodynamics to study heavy ion collisions, we're also using heavy ion collisions to study hydrodynamics and to push the boundaries of our understanding of hydrodynamics, of relativistic hydrodynamics. Now, effectively, what you end up with is that you have a certain energy density profile at early time for your quark-gluon plasma. This is given by different models that we have. And then we describe how it evolves in time with relativistic hydrodynamics. It yields profiles like this. You can see this is a cut in the transverse direction of a plasma. So if you're two nuclei are colliding like this, you take a cut in the direction transverse to the collision axis. So you can see the plasma has a certain extent, it has certain fluctuation, and you look at how the energy density evolves with time. And all of this is given by hydrodynamics, given a certain initial condition. So you can see that the plasma actually cools down very quickly. So there's the regions are at very high energy density are relatively limited, and very quickly you're in this what I call a crossover region here. There's this phase where it's difficult to say if you have if you should use really quarks and gluon as degrees of freedom, but you can think of it as a glue of strongly coupled quarks and gluons, and you have this slow transition to hydrodynamic degrees of freedom. Now, to effectively constrain the viscosity of the plasma, what you do is that you change the viscosity and you see what effect it has on the evolution of the plasma. And by changing this viscosity, of course, we don't have direct access to this profile of the plasma, but we have access to the pions, the kaons, the protons, the photons that are being measured by the detectors. So by changing the viscosity, you change this profile, but you also change the momentum distribution of these hadrons. You change the correlation that they have. And by comparing with data, different, you run the calculation with different viscosities, you compare with measurements, and that gives you a constraint on the shear and the bulk viscosity of your plasma. Now, for the rest of this talk, I'll present a result that I obtained in collaboration. It's a result of a collaboration of people all over the US and Canada, including many people in Berkeley. And what we did was to take a set of measurements from both RIC, the particle collider in the US, and the LHC, the one in Europe. We took different types of measurement. For example, number of pions that are produced in the collisions, number of kaons, number of protons, and each carry different information. We looked at the average momentum of these hadrons. We also look at the momentum correlation between different hadrons. And what we did was to parameterize the viscosity and then perform a Bayesian inference to constrain this parameterization to the data. Now, it is a challenge to parameterize the viscosity. The viscosity is temperature dependent. There's expectation that the bulk viscosity of a plasma has a peak in the confinement region. The argument being that the bulk viscosity is related to the conformality of the plasma. And at very high temperature, QC is nearly conformal, but this conformality is broken, especially badly in this the confinement region. Now, the fact that you have a peak doesn't mean that bulk viscosity is large. So the question is, what is the shape? Also, what is the magnitude? So what we did was to make sure that our parameterization could accommodate for large and small values of bulk viscosity. It would go to 0, which is the theoretical expectation at high temperature. But it was flexible enough to have possibly an asymmetric shape in temperature above and below a certain peak. For shear viscosity, again, we know what the behavior is at very high temperature, although we don't necessarily know what it is at the highest temperature we're interested in. Just remember that temperatures I'm showing here, this is 400 MeV. It's still extremely small. The coupling is still very large at 400 MeV. So it is still a very small temperature in the absolute scale. So while we have calculation of shear viscosity at very high temperature, they don't necessarily apply here. But we do have an intuition that viscosity should increase past a certain point, and that viscosity also increases at low temperature. So we expect that we have a peak in bulk viscosity. We have a minimum in shear viscosity, and that's the parameterization that we use. We use very flexible parameterizations. We actually did not force the parameterization to have a minimum here. We allowed these slope to vary in a wide range of values, such that you could even have a peak if you wanted in shear viscosity. I'll show later that actually data does prefer a shape that's similar to the theoretical expectation. Let me skip this here. So what's left to do once you have a model of the collision that includes the early stage of a collision, you have your hydrodynamic evolution, you have your hydrodynamic transport, and then you compare with measurement. What's left to do is to compare with measurements. So this is the result of the analysis that we did. And this is a summary of the data that we compared with. So these are the number of different type of hadrons, the average energy of those hadrons. This is a type of fluctuation in the energy of the hadron between, so every collision has a different number of hadrons. All of these hadrons then have different energy for each collision. You can look at fluctuations, and this provide constraint in the same way as other measurement provide constraints. These are the Vn, they quantify correlation in the plane transverse to the collision axis. And the bottom line, there's a lot of information on this slide, but the bottom line is that you can see the lines here are the result of our calibration. They're the result of the comparison of our model with data. You can see that we get a very good agreement with measurements, both for a DLHC and for RIG, for the US Collider. Now, these results are from this paper here, which is a result from the Jetscape Collaboration. As I said, these results were performed, so a large number of people were involved in the analysis, including, I'm sure you're all, I'm sure you all knew Wei Yao, who just moved from Berkeley, who spent a couple of years in Berkeley as a postdoc, and there are also I think Xinyan's on the call, and I'm sure others are on the call in the author list here. I won't walk you through this entire paper. There's a lot in there. The reason it's such a massive paper is not that it's the first model to data comparison. It's that we used a Bayesian framework to do the model to data comparison, and we tried to do it in a very systematic way. It's not the first Bayesian comparison with data, but I'd say it's the most complete one that has been done yet. We're very thorough in terms of selecting our model, which I've described only briefly, but there's a number of different choices you can make in your model. And we've been very careful in the selection of all the different stage and even of the translation of the shear and the bulk viscosity. We paid a lot of attention to priors, which, if you're familiar with Bayesian inference, you know this is a subtle point in Bayesian inference that you really need to be careful about. If you have a question about priors later, I'm happy to discuss more. We've performed closure tests, which is a way to make sure that if you perform a Bayesian analysis on your own calculation, you can recover the parameters that you put in. So essentially, it's a way to validate your entire analysis before you compare with data. And interestingly, it hadn't been done in our field before us, and we found it extremely useful, and it really gave us confidence in our analysis. We perform what is called a Bayesian parameter estimation, which is when you extract your parameters, so you extract your shear and your bulk viscosity from the data. But we also looked at sensitivity study, which tells you how sensitive are different parameters on different measurements. There's more. We perform validation of a model and so on. Again, if you have questions, feel free to ask later. Let me focus on the result of the analysis, which is essentially which parameters are consistent with data, but by including both the experimental and the theoretical uncertainty in a systematic way, which is something that is typically not done when you do model to data comparison just by hand. If you do what people call a chi by eye, which is you try to adjust your model parameters and you try to fit roughly to the data, there's a number of intrinsic bias that you have. You tend to ignore the size of uncertainties beyond a certain point. You can't necessarily account systematically for all your uncertainties. And a Bayesian approach is really a way to not only to do all of this, to include your experimental and theoretical uncertainty, but it's a way to do it systematically in a way that's reproducible. So you have essentially a recipe. As I've already shown, we get a very good agreement with data. The viscosity that we found that has this good agreement with data are shown here. So this is the bulk viscosity and this is the shear viscosity. So first notice the small range of temperature that I'm showing. So in the paper, we actually show a slightly wider range of temperature. And the reason I'm only showing this range is that really above 250 MeV, we have very limited constraints on the bulk and the shear viscosity. You can see that bulk viscosity that we found is around 0.1, 0.05, 0.1. The shear viscosity is also around 0.01, 0.2. Just for reference, the 1/4 pi that's often quoted is somewhere around, it's just slightly, it's 0.08. So it's slightly smaller than this. You can see that the constraints, as I said, are limited. There's still, and it might seem even disappointing that we can't obtain better constraint than this. There's a reason why our constraints look like this. And they're actually wider, they're actually less constraining than previous analysis that have been done before us. And the reason is that there are two ways that you improve constraints on a property like the shear viscosity when you compare with data. You can include more data in your analysis, and the more data that you include, the stronger the constraint you obtain. And that's almost systematic. You add more data, you have more constraints. So what you do when you add more data is that you increase the precision of your analysis. Now, what we focused on in our analysis was accuracy. We really tried to include as many model uncertainties as we could. Model uncertainties include anything we don't know about exactly how the energy is deposited in the collision. So you need a flexible model that can account for multiple configuration of energy deposition. It also includes uncertainty from the transition from hydrodynamics to the hydrodynamic transport. Hydrodynamics describes your energy momentum tensor. It's a coarse-grained description of your plasma. Now, when you transition to particles, what you need to do is you need to define a hydrodynamic momentum distribution for all these different species of hadrons. And in a way, you don't have enough information from hydrodynamics to do this. So you need to complement this with a model. You have to know, in principle from QCD, if you have a plasma of quarks and gluons at a given temperature, or a plasma of hadrons at a given temperature, how energy and momentum is distributed among these hadrons. And of course, in the thermal case, we know, in the perfect ideal hydrodynamics case, we know that your hadron should be disputed, should have a thermal distribution, Bose-Einstein, Fermi-Dirac. The challenge is that we don't expect perfect, of course we have viscosity here, we don't expect perfect local thermal equilibrium in the medium, which means that you have a certain deviation from your local thermal equilibrium. And that means that you don't have Fermi-Dirac distribution or Bose-Einstein distribution for your hadrons. This is one source of uncertainty. There are different models that can be used at this stage. And the bottom line is that there are uncertainties in our model, and that you have to be extremely careful. It's possible to obtain a very precise and very inaccurate result for your shear and your bulk viscosity. You can easily end up in this corner if you're not careful. We have broad distribution because we decided to go in this direction. We use measurements that we think are less sensitive to model uncertainty, and we made sure to include as many model uncertainties as we could. So we ended up in a region like this, where we're more confident that the real viscosity of QCD is in our confidence interval. But of course, our confidence interval is relatively broad. Now notice that at high temperature, the viscosity is somewhat, the constraint on viscosity is not very good. And there's a number of different ways of adding constraints. I'll just say a few words about something that I've worked on personally, but of course you should understand that there are many different types of measurement that you can add to increase your accuracy. So one possible way of adding measurement and adding constraint at high temperature is to look at photons. So photons are produced throughout the collision, and a large number of photons are measured in heavy ion collision. Most of those photons actually come from hadronic decay, so they're not necessarily that interesting. But the small numbers are actually radiated by the quark-gluon plasma itself at earlier time. And there's hope that because they're produced at earlier time, higher temperature, they would be more directly sensitive to the shear and the ball viscosity at high temperature. Now, of course, everything I've just said about theoretical uncertainty remain the same. One of the reasons that photons are not yet in Bayesian inference is that we do think that they have significant theoretical uncertainty. But of course, we should still study how they can be used to constrain the shear and the ball viscosity. So we know that there's photons that are being produced by the quark-gluon plasma itself, and we know this can be measured. I believe that I've seen Wenching on the call. So this is a plot from her talk at Quark Matter in Wuhan. So effectively, what we know is that we have an idea of how many photons are produced if you assume that there's no quark-gluon plasma produced in your heavy ion collision. And this is this background in yellow here. And what is measured here is the actual measurement of photons. So you can see what doesn't look like a big difference, but of course you have to understand this is a log plot with 10 orders of magnitude. So there's a massive number of photons that are missing actually, if you assume that they're just produced from normal non-quark-gluon plasma sources. And it's possible to estimate photons that are coming from the plasma. And if you do, you obtain results like the one that I'm showing here, where you have this background that you expect if you don't have a plasma of quarks and gluons. You have, if you add the photons from the quark-gluon plasma, you have this black band, which is in better agreement with data, both at RIC and at the LHC, as you can see here. And again, remember, there's 8 orders of magnitude here. So it doesn't look like a big difference, but it's a large number of photons that are being produced by the plasma. And it's possible to show that these photons have a sensitivity to ball viscosity. What we see is that, for example, the ball viscosity tends to reduce the blue shift of the photons. So you end up with more photons at low energy and less at high energy. Now, we're not yet at the stage of, I don't think, of including photons in large-scale constraints of the shear and the ball viscosity. But they're one of many tools that can be used to increase our constraints in the viscosity. So I just want to end with this slide before my summary, which shows how, despite the fact that most of my talk has been about those low energy hadrons that are produced in heavy ion collisions and how we can use them to constrain the viscosity, there's a large number of other probes, of other messengers. We have photons of different energy. If you look at higher energy, they're more sensitive to earlier stage. If you look at higher energy, they're more sensitive to the earlier stage. At lower energy, they're more sensitive to the later stage. You have dileptons of different mass. You have jets, of course, which are high energy hadrons. You have photons, C and W bosons. And we're slowly trying to combine all of this information into better constraints on the viscosities. I think the bottom line, what you should remember here is that we are now in a position to extract very systematic constraints on the shear and ball viscosity of the strongly coupled quark-gluon plasma using measurements from heavy ion collisions. There's still information that we need to fold in, but really the question is, how accurately can we measure the viscosities? And what we have to aim for is both precision and accuracy, which is, to a point, an open question. So a lot of the work being done in the field is to improve the models that improve the accuracy. There's work being done on finding new measurements, and that increases the precision. And all of this combined, we hope that we can obtain much better constraints on the shear and the ball viscosity. Let me stop here. I'm happy to take any questions that you have.
All right, thank you for the very nice talk. It's very interesting. Do we have any questions from the audience? Olivia, you have a question?
Yes, thank you. Yeah, for the nice talk. I had a question whether transverse momentum differential observables are considered and what their effect might be. In particular, I think there was a work by the trajectum group, and the takeaway I think that I got is that bulk viscosity, basically the extracted value drops if you consider transverse differential momentum differential observables rather than integrated ones. And maybe you can comment this. Thank you.
Yes, so the question is, so of course, there's a large number of measurements that have been made in heavy collisions, and the analysis here used a subset, a small subset. In particular, here you can see we use PT integrated observables, so momentum integrated over the transverse energy of the particle. You can also look at either PT differential observables, or you can simply look at higher moments of your, so you could look, for example, at PT squared or PT cubed. So the question is, what happens if you include this kind of measurement, this kind of data in your analysis? So the reason, so I think that the answer is, if you include them, you get better, you go exactly in this direction. So you get more precise constraints on your viscosity. The reason we didn't do it is that higher PT particles are more sensitive to theoretical uncertainties. In particular, they're much more sensitive to this uncertainty in the transition from hydrodynamics to hydrodynamic transport at the end of the collision. So what they find is that you need a smaller viscosity. You find a smaller viscosity if you include this PT differential observable. That's roughly my expectation, because we know that our model tend to overestimate the effective viscosity on these observables. And in particular, the model that they use tends to really amplify the effect of ball viscosity at high PT. Now, is it physical? Is it an artifact of the model? I don't know. I'm worried about using at least a single model and extracting viscosity using a single model, especially if different models that we have no reason to believe one is better than the other produce very different results. So I'd say in summary, I'm not surprised that they found a lower viscosity. I don't know. I think we should be careful about concluding that this is the viscosity of QCD. That's the viscosity you extract from the model. I don't know if that's the viscosity of QCD that you're extracting.
Mm-hmm. Well, this is of course the issue for any analysis, I guess.
Yes. Yeah.
So would one of the things then to mitigate this potential systematic errors in the model is to put a cut on the higher values of PT that are considered in this type of analysis?
I mean, it's a way you can, to be fair, I think they've been careful reproducing the analysis with different cuts. So it's a good question. Should we exclude data, or should we try to improve our model to describe this data? I think we should try to do both. I think probably what they should do is try different models of hydro to transport transition to make sure their results don't depend on this. And what we should do is to add this data in our calibration here. And if we find that we have a very large dependence on the model uncertainty, maybe it's a reason to not include the data in the results. But I think we should do both. Yeah.
Okay, thank you.
Xinyan, you had a question?
Yeah. Oh, sorry. There's not about noise in the background. So I'm not sure we have discussed in the paper. This is the range of temperature that this observer was sensitive to. This for example, this LOS, and now you're only limited to like up to 250 MeV. I would imagine normally. I would imagine normally, especially at LHC, the highest temperature is much higher than this. And the reason why there's not much sensitivity is this because all the observers you're looking at are not really sensitive to how the system evolved in this very highest temperature?
Right. So I think actually this relates to the question, the previous question. I think in part it's because we picked observables that we thought had less theoretical, we could reproduce with less theoretical uncertainty, but had also a more limited dependence on viscosity. So in a sense, we created this problem. We picked observables that probably are not very sensitive to the viscosity at high temperature. I think in part, there's also, I mean, we do expect that hadrons have very limited sensitivity to high temperature viscosity. There's so much evolution that happens before hadrons are produced that it's probably difficult to, you would expect it's very difficult to pinpoint accurately the viscosity at high temperature just from hadrons. Now, I think sometimes we're misled into thinking we can because we fix certain, for example, we fix the initial condition, and then maybe we find only a certain parameterization of viscosity that can fit the data. Maybe this parameterization is well constrained at high temperature. But I think once you account for a lot of the uncertainties in the model, it's actually quite difficult to constrain with just hadrons.
Yeah, well, I mean, you at the end you pointed out that, for example, direct photons probably is a different story because there the emission rate is the highest at at very high temperature, maybe.
Yeah, the real question, I mean, we really have to keep including more data, but we just have to do it carefully so that as we include more data, and of course, this is always model dependent, but we know there's uncertainty, there's known unknowns in a way. And ignoring those known unknowns when we add the data to the analysis will just mislead us. It will just lead to values of viscosities that have little to do with the actual QCD viscosity. But yeah, we probably need more. And to be fair, some people think like HBT, which is a purely hadronic measurement, could constrain at higher temperature. So it's possible that other hadronic measurements can constrain at a higher temperature. And also, of course, jets can help too.
Well, jets is a different story. I mean, if you look at if you want to extract the temperature dependence of the transport coefficients, Q hat, for example, and there is different story, and yes, because it's much more sensitive at high temperature than low temperature, in fact.
Yes, because of the
energy loss, in the beginning.
The dependence of the energy loss, yeah, it's very different. Yeah.
Okay, thanks. Yeah.
Sure.
Okay, any more questions from the audience? If not, I have probably a simple question. So for this shear viscosity, we're talking about this 4 pi asymptotic limit. Is this a strict limit for QCD, or is this something that you don't necessarily expect to be true?
there's a long and a short answer. So I think the short answer is we don't expect this to be an absolute limit. Of course, QCD is not conformal. There's been work being done that show that in different field theory, you can actually get lower viscosities. There are still general arguments that say that your viscosity shouldn't be much slower than 1/4 pi. Just from there are other arguments based on the fluctuations that you have in your system and so on. So it's not an absolute limit based on this ADS-CFT calculation.
Mhm.
The ADS-CFT calculation is at least suggestive there might be some limit. And there are other reasons to believe there are limits around that value. So I'd say in general, we do expect that there's a limit, probably around 1/4 pi. It's a combination of arguments that are not necessarily all from the same direction, but I think we have a pretty good reason to believe that the viscosity shouldn't be much lower than 1/4 pi.
Right, okay. Yeah, the reason I was thinking this is that, for instance, on this plot here on the right, you have that there's at least some of the 90% credible limit below this limit. So if it were a strict bound, you could maybe think about using a log normal prior or something that is strictly bounded and stick that in. And that could reduce the uncertainty without actually introducing any model dependence if we know that that's a strict bound. But
yeah, no, that's a very good point. I've mentioned priors earlier. So I mean, in physics term, if we know that the viscosity has physical constraints that are from not from the data we're looking at, but other theories or other calculations, we can enforce those constraints, as you just said. We actually decided not to. For example, most people think that the viscosity has to increase at high temperature, and there are relatively good reasons to believe this. So we could have excluded every possible dependence on shear viscosity that decreased effectively at higher temperature. We decided not to do it because we thought it's more informative to see that. So basically, if you force it, you don't know if your data favors that or not. But if you don't force it and you observe that it actually does look like the viscosity is going up, then, or at least that you're excluding small viscosities at high temperature, then you in a sense you have more information. Yeah. But if you strictly speaking just want to get better constraint on your viscosity, you should actually have stronger priors, just like what you said. Yes.
now, before you showed at least one model where it had this kind of kink in it, and it looks like that kink is reproduced in that plot of your actual posterior. So I guess my question is, if you moved the kink in that prior, would that also move the posterior kink?
So we
well?
varied the position of the kink. So the posterior that I'm showing here already includes the variation.
You're including that in that.
Yeah, it includes it. Yes.
Okay. Yeah. I should expect that, but
no, it's I think other analysis don't do it, actually. I think we're the only one that have varied this position of the kink. I think it could be important. I don't know if it's essential, but I think it could be important, at least because we don't necessarily think that the kink, we don't necessarily know at what temperature that the kink has to happen. It could happen at anywhere between 150 and 200 MeV, I think. So you probably want to vary it.
Yeah. Okay, last chance for questions from the audience. I don't see any, so let's wrap up here. So thank you very much. It's a very nice talk.
Thank you. Thank you again. Have a good one.
Yeah, you too.
Bye-bye.
Take care, everyone. Bye.
Bye.
Thank you. Bye.